If you've ever designed the LLC or the LCC converters, both resonant converters, you'll find this topic very interesting, I'm sure. My name is Wendell Boucher. It's the 14th of July, 2016. First, we're going to briefly compare the resonant LCC converter with the LLC resonant converter, the most popular one, of course. Each has its own merits. The LCC is ideal, however, when using step-up transformers, and you always use step-up transformers when generating high voltage. And sometimes when you're generating low voltage as well, of course. So we're going to focus on the resonant LCC topology design by demonstrating these things. Number one, how to define the power versus frequency curve to yield a producible design using component values within a tolerance of plus or minus 10%, which is quite practical. Then we're going to assign the resonant part values and primary voltage to yield the desired power versus frequency curve, which we defined here. For our example, this took about 15 minutes to do. Then we will run a program that plots the power versus frequency curve for the LCC design that we came up here. And we're going to do it at low line, nominal line, and high line. So we'll have sets of data to compare. The set produced with this software and the set produced with this. Then we will show a plot of the closed feedback loop, gain and phase, and performance data as well to compare with the state variable predictions, namely these two programs. And finally, we'll run an LT Spice simulation model of the power stage and look at its performance. You will then see that all four demonstrations produce data that compares within 2%, which is very good. In fact, it's a lot less than this. It's usually within 0.5%. Calculations to this degree of accuracy, of course, translate into high production yield, which is the main objective of any engineering design effort, of course. Now I'd like to expand a little bit on what the LCC really is and what we're doing here. So please note that the LCC design program actually performs the time domain analysis of an LCC topology. That's why it's so accurate. This is a topology of at least the fourth order. My method handles a system up to any order because of the unique state variable approach. And this is what's done. In short, all coils and capacitors are replaced with a resistor and state battery. This yields a circuit which is easily solved using any appropriate method. For example, Gauss-Seidel, matrix inversion, or Millman's theorem. Also note that the LCC is a very attractive topology to use when transformers with a step-out turns ratio are employed, as I said before. For example, in high voltage power supplies. The reason for this is that looking into the primary of a high voltage transformer, you do see an unusually high capacitance. For example, for a 1200 watt power supply driving a TWT load and wound on a UU64 core set, the capacitance called CEP is usually about 0.01 microfarad to 0.02 microfarad. That's very typical. However, the LCC absorbs both the leakage inductance LLP and the capacitance CEP so that they are simply design parameters when you design an LCC. When the LCC is used with unity or step-down transformers, however, the capacitance CEP must be provided with an external capacitance connected to the transformer secondary. And because of this, other resonant topologies can be used. For example, the LLC itself, another resonant topology, or the resonant transition phase control topology, and others. Now very briefly, here what the two topologies look like, schematically speaking. This is the LLC. It derives its name from the fact that there's a L, another L, and a C in the resonant circuit, this circuit. The LCC derives its name from the fact that there are two capacitors, this one, and one inductor. This inductor is important, but nowhere near as important as this one is. This is the primary of the transformer. Now this is what's important here. FHA stands for Fundamental Harmonic Analysis. It's a technique for modeling both the LCC and the LLC to produce a curve which is a frequency versus power curve, which we're about to derive. Unfortunately, it's known to be rather flawed. So the method used here is the author's state variable method. Accuracy is not an issue, and the reason is that the model is an actual time domain circuit. So it is just as accurate as any SPICE-like software, such as PSpice or LT Spice, to name two. Now we're going to cover this topic: how to define the power versus frequency curve to yield a producible design, as I said before. So let's go down and look at that. Here's what a typical curve looks like for an LCC. The LC is very similar, but we're talking about an LCC here. This is a curve in which the y-axis is power output, the x-axis is frequency, with increasing frequency going in this direction. See this little arrow? And we work on the high side of the peak power number. This is the low side, this is the high side. We'll call this frequency FP for frequency peak power. We'll call this frequency a set frequency. I'll explain that in just a minute. We'll call this a run frequency. And this is the frequency which we run at full power and low line. This is a worst case condition, of course. Now, what we'd like to do is look at this frequency and then set this frequency to a number which is about 0.85 times that value, which means this frequency is about 15% lower than this one. That's to allow for component tolerances, and so is this one. We'd like this one to be another 15% lower than this one, or saying it another way, we'd like this frequency at the peak to be at 0.7 of this frequency. 0.7 times 5 is 35 kilohertz, or lower. And we'd like the frequency at which we deliver no power at all, or zero power, to be set some reasonable value above this one. In this case, 100 kilohertz is quite reasonable, where we deliver 0 watts, but we're regulating the output voltage. A couple of other things I can say about this. The distance between these points, frequency-wise, is set by the ratio, or can be set by the ratio of two capacitors. Go up and show those to you. See this capacitor and this one? This one should always be larger than this one, and the larger this one is compared to this one, the wider will be this distance and this distance. So for our design, I picked the frequency of 50 kilohertz to run at low line and high power, and 100 kilohertz, but I usually don't do this. As a matter of fact, I've never designed one using these two frequencies. Usually I design this to be 100 kilohertz, It's a nice round number to remember, 100 kilohertz, and I usually keep this below 230 kilohertz. That's what I usually do. The reason I picked these numbers is because I wanted to run the program that sets the reactive values for us, resonant values. I wanted to see how long it would do. Or take to do, I should have said. And in this case, it took about 15 minutes. I didn't want to be biased by using numbers I'm used to. Hence, it's the reason for using 50 kilohertz and 100 kilohertz or less. Now you'll see on the screen a design program. This is it. It's written in my own state variable. It executes very quickly. It's very, very accurate. I'm going to show you how accurate in just a minute. So let's stop this for a second. This is actually the answer, of course. I'm going to show you how it was done in a moment. We're showing power versus frequency for DC line variations of 255, 300, and 345 volts. The state variable design program is set at 50 kilohertz at 255 volts, 54.2 kilohertz. This is the one that's set. This is what we calculate. The only one we set is this one. We calculate this one and we calculate this one. But here are the numbers. At 300 volts line, we are to operate at 54.2 kilohertz. At 345 volts line, we operate at 57.4 kilohertz. Now, we mentioned before that we have a closed loop design, and because it's a closed loop, it's going to regulate the output voltage to exactly 300 volts by design. And when we do that, then we can look at the frequency it came up with. We have no control over this. The closed loop does. And look how close these are. We want 50 kilohertz, we got 49.87. We wanted 54.2, we got 54.187. We wanted 57, we get 57.409, or 57.4, 57.409. Here's the difference between these two numbers. In this case, it's only 0.26%, 0.02%, 0.015%. FHA can't even come close to this. Then we did something else. We looked at the graphic plots, which are a little more crudely done. It was done using the state variable program, of course. We had to play some tricks to do the plots. In the programming, that is. Nevertheless, here we go again. 50 kilohertz is what we want. We got 50.366. Because it's hard to read this curve, this number goes all over the map, of course, but this one kind of stays the same. We wanted 54.2 by design. So that's what it said we're going to get. We got 54.349. We wanted 57.4. We get 57.574. Here are the errors. Again, well within 1%. I was guaranteeing 2%. Okay? Now let's take a look at the state variable program itself. Remember, we wanted to match a curve. So what's important to us is power versus frequency. When we ran this program, you can see this is frequency in kilohertz, power output in watts, and we've designed this for a kilowatt, of course. You can see at 50 kilohertz we have a kilowatt within 3 watts. But besides producing this data, we produced a lot of other data, and this is perhaps the best application you can have for my state variable technique is when you're producing a lot of data to look at. Of course, our first task was to match this power to this frequency, but after we do that, we look at these numbers. For example, this is the capacitor voltage, and that's the series capacitor. This is the peak voltage we see. We're going to look at some of those numbers in a while. This is the voltage across the series inductor, resonant inductor. Again, the peak value. Now this is the flux density if you have 1 centimeter area and 100 turns on the inductor. This means when we're running at this voltage and this power at this point, we have to calculate the losses for 1,846 watts if we had 1 centimeter and 100 turns. Excuse me, a mistake. I just had a verbal typo. This is at Gauss, not watts. This is at Gauss, not watts. This is the current passing through the series inductor and through the series capacitor as well. So at the high power, we see it's about 6.08 amperes RMS. We'll show that to you later also. Here's the FET loss for a RDS on of 0.34 ohms per FET. There's 4 of them in the bridge. Now we can reduce this number, of course, by reducing this number. And we could have done that, but I wanted to show it to you with a value that happens to be in the computer library already. And this is the flux density seen at the primary of the transformer. So if that transformer had 1 centimeter of area and 100 turns on the primary, we'd be operating at 1200 Gauss. So obviously we're going to change, in both cases, we're going to change the area and turns to suit our needs accurately. I'm going to run this program for you. Click here and you can see the line appear. F star can be anything, so let's take a real close look at this one. Let's type 50 kilohertz, 0.1 kilohertz, and 51 kilohertz. Low line is 255 volts, and the primary voltage is 300. That's what these numbers all stand for. We'll run it. It's done. See how quickly that did that? So we're really running at about between 50 and 50.1 kilohertz. You can see these numbers. Now, let's look at another program. Bring this one up. And we're going to run this program, explain it to you in just a moment. Move this up a little bit. Now you can see here the resonant components, 0.2 mic, 230 microhenries. CP is 0.0, I'm not sure that's 0.06. Wait a minute, let me look at that. No, that's a typo. I have been using that value before. You see this value here, 14 nanofarad? That's actually 0.056 here, so I'm going to change it for you. That's simply a typo, by the way. The number it's really using is this one. But it looks like 0.056 looking into the primary, but it's on the secondary. want to bring this up again. You see three curves. Look at these numbers in the x-axis. They actually stand for 40 kilohertz, 50 kilohertz, 60 kilohertz, 70 kilohertz, 80 kilohertz. Now remember that we wanted to design so we got 1 kilowatt at 50 kilohertz. This is the low line curve, power curve. You see it peaking right here, well below where we're going to operate, which is about in here and here. So let's take a look at that more closely. Or let's look at all three of them more closely. That's even better. Let's draw a line right here. What we're seeing is that when we want to operate a low line, we're going to have a frequency right there at 50 kilohertz, like we designed it. Another frequency over here at 54 kilohertz, roughly, when we're at nominal line, or 300 volts DC. When we're at high line, we'll be operating at this frequency, 57. Now I plotted all that for you before. Show it to you. Right here. Excuse me, it's not that one, it's this one. This is one compared to this. Graphic plots, what we're looking at. These are graphic plots. Now this could be used as a design program, but I prefer to use this one because it yields so much more information for us. And it was the first one I ever used, by the way. You can see we have zero power, even in high line, that's this one. And in all cases, the peak is well away from where we're operating. Now, I'm going to show you another program. And by the way, let's show you the setup. Setup multi-step. There are the numbers, 255, 300, and 345 volts. Somebody told us to run it. I'll do it again for you. I say run multi-step. And there it is. Low line, nominal line, and high line. Such data is useful for reports. Now I'll show you another program. This is the same design, but with a closed loop now. Has the proper capacitor value on the secondary, 0.056. I chose that, by the way. This is what you have to do when you design a power supply. You have to use values which you can actually purchase. So we have to design our own capacitors. So I'm using these capacitors. Using one of these and two of these. If I were operating at 100 kilohertz instead of 50 kilohertz, I only need one of these. So let's go back up. Now we're going to run this program. I might point out that we can run this steady state or AC or transient. Here are the simulations, for example. Choose analysis. We have these three. The pop analysis takes the system to steady state. Does it seconds. So I'm going to run that first, right now. It's finished. Let's look at some voltages. Here's the output voltage. We wanted to regulate to 300 volts. We're regulating it to 299.99973, which is pretty close to 300. And now let's look at the frequency it chose, because, well, here's the feedback loop down here. We're simply using a UCC 1806 chip and going into the RT terminal and vary the current at that terminal in the feedback loop. That's how we control power. This is a type 2 compensation amplifier. Sense the voltage here into the compensation amplifier. Compare it against a reference. This is slow start design. I'll show that to you in a minute. But let's look at the, for example, the current to this inductor. We have it up there. Let's look at the RMS value. 6.058 amperes. Remember that. 6.058. We'll go back and look at this one. .08. Pretty close. Two separate programs calculated this number. One is 6.08, the other one is 6.058. All right. Now, since we have a closed loop, we're going to show you the loop analysis. And that's done by changing the design from this to pop to AC and running it. And do this to put both curves on the same scales. You can see we're crossing over at about 4 kilohertz. Let's see, what line are we running at? We're running at low line, 255. You see this number up here, 255, that's low line. You can see we have a good phase margin, about 70 degrees, good gain margin, roughly 17 dB, right about here. Let's run that again. We'll change the line voltage now to 300. Now, I have to change the analysis to transient. I'll show you why. In fact, I'll do it. Let's leave it right where it is and run it. This sometimes happens with this program. Well, it's running just fine. Now, you can see it's almost the same loop. And there it is. It's almost a -1 slope. Frequency's moved up a little bit, as you can see. Now, let's do it at high line, which is 345 volts. I'll run it again. Now you see, it didn't run that time. So what we do is change the analysis to a transient analysis. It's done this quickly. Now let's run the transient analysis. In fact, here's the output voltage. We're running into 300. You see the slow start. Now we're going to change it to an AC analysis because the program remembered all of the operating points. And there it is at high line. So you can see nothing strange is happening when you close the loop of an LCC. But while we're there, let's do something else. Let's look at the frequency. We have to change this back to a, well, there's another way to do it. I'll show you. Under this one, we can do pop voltage. We'll do it right there. And we'll measure the frequency. 57.4096. 57.4096. Where have we seen that number before? right here. When we run the design program, we get 57.4. When we run this program, we get 57.409. That's 0.01567% difference. Not very much. Now we're going to show you the last calculation. First, we're using the design program again, focusing on a DC line voltage of 300 volts. Of course, a load voltage of 300. And at about 54.2, we're calculating pretty much a kilowatt of power. So we're going to run another program. This is the LT Spice program. Now notice something. Focus this again. 54.2 kilohertz. We're predicting here. Now, so we set this one. I'll expand it for you. 54.2 kilohertz. This is just a power stage. No closed loop, as you clearly see. Now, we're going to run that. It's been run already, but we'll run it again. It's running, it's finished. And we're going to look at the load power. We click on that. You look here, let's see, it's 999.25 watts. We designed it for kilowatt. Very close. So using the design number here, we've proved that design is solid. Look at some other numbers. Let's look at this inductor current. Look at the top of it. See what the number is. Let's see. I didn't mean to look at the top. I meant to look at the RMS current. We're going to look at it right here. Calculate it. You see it came up 6.51 amperes. 6.51. Remember that number? And here we are. 6.52. 6.51 is here. 6.52. Very close. This is what we calculate. This is what we measure. Let's look at some other numbers. For example, look at the capacitor. I'll get rid of this one and look at the voltage across the capacitor. You simply click here, there's the voltage. Now the design program tells us that that voltage peak should be about 136 volts. So let's see what it is. About 135.8. You look down here, there's a number, but you can also see it over here. The number actually is 135.78 this time. Can't do it quite that accurately, but 135.72. And we calculated 136. The voltage across the coil we calculate to be, by a design program, 736 volts. Let's look at that one. Here it is. 736.8 right here. 736.8. And one final calculation, let's look at the dissipation of the FETs. If you look at these FETs, you will see that they have an RDS-on of 0.34 in the LT Spice model. So let's look at the power level. There's one. Gotta go up here. And here's the other. I'm going to have two numbers. 6.369. 6.369 plus 6.3086. 6.3086. I did that correctly. We got 12.67. We multiply it times 2 because we have 4 FETs. And we come up with a number which is 25.355. Now let's compare that 25.355 to the number we actually had predicted with the original program. And here it is, right here. The power is somewhere between 25.7 and 25.8. 25.355 is right in here. We're about to wrap it up. I think you've seen the accuracy of the state variable method compared to the FHA method. I didn't show you that, but you'll find a lot of information on the web describing how inaccurate it really is. So I thought I'd leave you with a passing thought. This is something I notice more and more. I have noticed that many design engineers in the power electronics field, my field of course, seem to be somewhat uncomfortable when dealing with the following subjects. Number 1, the design of magnetic components used in switch mode power supplies. I was fortunate because my career started designing pulse transformers, and switch mode power supply transformers are almost identical. I'm happy here too as well because I started in simulation in a very early age and continued on. This is another subject, simulation and modeling, to the extent that the predicted and actual measured performance agree within the tolerance of the parts used. For all practical purposes, my designs always meet this criteria, because I go the extra mile to use real models. Capacitors, for example, are not just capacitors. They have resistance and inductance as well. The third one is closing feedback loops accurately and with great confidence. Although I've done pretty well with these two, this one was a problem for me. At one time in my career, I too felt uncomfortable closing feedback loops. In fact, I had a friend and a colleague who would close the loops for me. We worked in the same company, so there was no problem doing it that way. Until one day we parted company. He left, I left, and I found myself consulting, and I had to close feedback loops all by myself. So I studied for about 2 weeks. At the end of that 2 weeks, I had no more problems. So I made the extra effort, as I said, to make sure that I can answer these issues with confidence. And to that extent, I want to expose you to this. Designing high-frequency transformers. That's the first one. I've created 3 general-purpose programs that will calculate both skin and proximity effects, losses in seconds, for any closely coupled winding configuration, which is the only kind you should use. in a switch mode power supply. These programs link to LT-Spice, free program. The conductors would be magnet wire, tape or foil, or Litz wire. Now this is what's unique. I read the output file generated by LT-Spice, which contains all the harmonics and their magnitudes. I use all of those harmonics to calculate the copper losses, and it does it in split seconds. And to confirm the accuracy of these programs when I was developing them, and I still do it to some extent, I use FEMM in Adams-Maxwell for magnetic field analysis calculations to look at eddy currents, skin proximity effects, that sort of thing. Also, I published a 190-page book entitled Advanced Magnetics Design Seminar at the Urge of Ericsson Electric. It's a magnetics design video called, another one, Reducing Transfer Losses Due to Skin and Proximity Effect. I did that quite recently. Can be viewed by typing that title on YouTube. Type this title. I'll show you later what you can do with these titles. Modeling and simulation. You can read this and you'll see that there's a link down here. I'll get those links to you in just a moment. And this is about the end of the presentation. Other YouTube videos besides this one you might be interested in and viewing are documented below. All you have to do is go to YouTube, of course, on the InterDupe, and then to view the videos, I could have given you the links, but I sometimes find they don't work. I don't know why. Two work and the third one doesn't. You have to type the label. Anyway, you simply type this. This describes what we're talking about. You type this for copper losses. And finally, this one I did quite recently, details the author's unique state variable method for performing circuit analysis of the time domain of circuits of any order. And that's the technique I used here. This is the method you saw used to write the LCC design program used in this video, of course. And if you have questions or other ideas to talk about, other concepts, I can be reached two ways. By email. This is my name, Wendell Boucher, wendell.boucher@comcast.net. Can be phoned. It's my home phone. I live in Bristol, Virginia, USA. Thank you very much for watching. I hope you got a lot out of it.